In this video, we'll be discussing the probability axioms and how they appear in the equally likely probability setting and what that means to be equally likely. So, just as before, we'll state the axioms right away. So let S be a sample space and let A and B events in that sample space, so they're just subsets of S. And a probability function P must satisfy the following. Basically, axioms in math are like saying this is the minimum amount we need, minimum amount of assumptions we need. And with this minimum amount of assumptions, we can create a whole system or whole systematic framework and theory. So when they say probability axioms, I'm saying, okay, I need some probability to satisfy these three rules. And if it does, then we get this whole thing called probability theory, a whole framework to work in. And those three axioms that we must have are that probability A of any event is between 0 and 1, just as we think of in terms of probability, right? We wouldn't say, oh, I think the probability is 1.5. Like, that doesn't make sense. You have to say 0.15. Or the probability that you make this shot is 50. Like, you don't say 50, you say 0.50, or maybe you convert it to percent. Secondly, is that the probability of an empty set, or pretty much probability of nothing happening, is 0. I guess that's not a great statement of saying it, but basically the probability of empty set is 0. And conversely, probability of the whole sample space is 1, being something has to happen with probability 1, and the probability of nothing happening is 0. I guess that's a better way of saying it. So the probability of, something happening in that process is going to be 1, and the probability of nothing happening is 0, because after all, it's an event and it's a random process or experiment, so something has to be happening. Although you could go on philosophical debates about this. Let's not go there in this video. And then lastly, if A intersect B equals the empty set, in other words, if A and B are disjoint sets, then the probability of the union of them is just probability of A plus the probability of B. So the union splits into a sum if they're disjoint. And that's a third rule or axiom that we need. All right, so that's the abstract notion of it. Again, I think an example will illuminate it. So just as before in our last video, we had our 6-sided dice rolled twice, and we recorded the pair. We have our sample space that we created last time, so I just made it ahead of time to save you the time. And the size of our set is 36. So all the possible outcomes in this situation, we can count them out or enumerate them, and that means it's 36. And then we defined two events. We said A is the event that they're matching numbers, and that would be, I think we used red last time, so we'll use red again. That would be this event here, so that's A. And then event A complement is the event that they're non-matching numbers, and so that's going to be kind of like this triangle that gets formed. I think technically it includes that one. And then, so kind of like two-sided triangles. And so that's A complement. So that's A complement, and we'll say that this is A. Okay. So I want to use the probability axioms to just apply to this event, kind of going back and forth between abstract and numerical. So something we can say about this situation. So by probability axiom 1, is it probability axiom number 1? No, I think it's number 2. Yeah, it's number 2. And since A union A complement equals S, we have probability A union A complement equals 1. Right? Probability axiom 2 says that probability S equals 1. That's what axiom number 2 says. All right? which makes sense in this situation, right? The probability that you either have matching numbers or you have non-matching numbers, well, that's the whole sample space. So the probability of that happening has to be 1. Okay, furthermore, probability axiom number 3 and since A intersect A complement equals the empty set, we have probability A union A complement equals probability A plus probability A complement. Right? Axiom number 2, or sorry, not axiom number 2, axiom number 3 says if they're disjoint, then you can just sum the events. That's basically what it says. Disjoint events, their union you can sum. All right, so now we have these two equations here. We have this one and this one, and they both have this probability A union A complement. So that means combining the two, I can say that probability A union A complement, which equals probability plus probability A complement, just by taking this identity here, equals 1, because that's what we said. Whoops, I don't know what that is. In other words, probability A plus probability A complement equals 1, which implies probability A complement equals 1 minus probability A. Right, and this is the complement rule. And so that's what I mean by axioms, is that from these 3 axioms, which again, axioms in math, you can think of as like the minimum number of rules to then create a system or framework. From just those 3 axioms, we now have a new rule that follows from and is valid in this system, which is this complement rule, which is very useful when it comes to calculating probabilities. What is this really saying? Well, for example, with numbers in the die, remember probability A, well, I haven't said this yet, but probability A, remember A is the matching numbers. You can think of it as, well, there's 6 events in here, in this A, and then there's 36 total. So if they're all equally likely, you can intuitively say that probably A equals 6 over 36. And that means probably A complement equals 1 minus probability A, which equals 1 minus 6 over 36, which equals 30 over 36, which matches the answer we would think. Right? If A was 6, that meant A complement would have to be 36. Or sorry, not 36, 30. So remember, this was A complement was size 30, and size of A equaled 6. And so intuition says, what's the probability of A complement? It would just have to be 30 out of the whole set, 36. And so it matches our intuition. These axioms, building with these axioms, somehow, I wouldn't say somehow, but miraculously or like amazingly create a system that is consistent with the way we would think about it. All right, so main thing to get out of that part was the complement rule, and that axioms create a system and framework, and that they match our intuition. Second part of this video right now is to hone in on what it means to be equally likely. And we used that here already, so I guess I kind of went a little backwards, or I went ahead before establishing everything, but I think it makes sense. So let's go ahead and establish what it means to be probability in equally likely setting. So let S be a sample space. An event, and A is an event. Then probability A equals, well, let's draw a picture of what I mean by all of this. So let's say this is your sample space. Those are all the possible outcomes, and let's say all these little dots, and they can be kind of scattered everywhere, but I'm trying to draw them the same size for the reason. Let's say these are all your outcomes. And let's say A is just some set, so it could be there. In an equally likely setting, all these little outcomes here that I drew in white, all these little dots, they're equally likely. So equally likely, they're all equally likely. And you can, it's hard to imagine like a space of like dots floating in the air, but you can really think of it as like a space of dots, and each dot is the same. And so another way is thinking that they have the same weight. Same weight, or maybe you think of them as having the same size. And so that they weigh the same amount in an accounting situation. And so if you want to calculate the probability A, you're really just thinking of like what proportion of these dots belong in this orange set. And that proportion is what equally likely setting is. So probability A is just the size of A. How big is the size of the set A over as a proportion over the size of the sample space. Okay, so that's what it means to be probability in an equally likely setting. And I just want to contrast that with, let's say you had a sample space, and I want to label it here as not equally likely. And if it's not equally likely, the vision you can have is that some dots are really big, meaning they have like a lot of weight or a lot of size, versus other ones are like really small. Some are medium, some are again like really big, some are small. And so that kind of looks like a Pokemon thing, but besides the point, they don't have equal weight, they don't have equal size. So the formula here that I'm using would no longer work, right? So in an equally likely setting, this is our formula. When it's not equally likely, you cannot use that formula. Not use probably A equals the size of A over the size of S. So that's a no-go. In this course, for the most part, I think we'll just be using equally likely setting. But just know it's still possible to compute probabilities. It's just not as easy as counting the number of things in your set that you're interested in, such as this orange one A, versus the whole set. It's not as easy as counting. What really happens is you have to somehow compute these areas and then take that over the relative size of the other areas. So it's totally possible, just something that we won't be doing.